distance time graph and speed time graph concept together. Okay, so that's why I'm drawing it in parallel. The information is found on page 14 and page 17 of your notes. So first of all, what is a distance time graph? A distance time graph has its axis, which I've already drawn. Okay, the vertical axis will usually be labeled distance, and then the horizontal axis will be labeled as time. Okay, likewise for a speed time graph, it will be labeled in this manner. Okay, so for the time axis, it really depends. Some questions they may start at 0. Okay, then after that they count in 1 hour, 2 hour, 3 hour. Okay, there are also occasions where they start off with maybe 9 AM. They write with the 24-hour clock, followed by maybe 10 AM, 11 AM, and so on. So these are the probable way of having your time axis being drawn. Okay, so you need to be able to read that correctly. Then for your distance axis, really depending, okay, maybe sometimes 1 km, 2 km, 3 km. So the units are maybe in km. For the speed, maybe, okay, depending on what you have, sometimes maybe kilometer per hour or meter per second. Okay, so we could have maybe again 1 kilometer per hour, 2 kilometer per hour, 3 kilometer per hour, and so on. Okay, just an example. So to draw the graph itself, okay, really depends on the question again also. Sometimes maybe you will just have maybe a diagonal line. I really am just anyhow drawing this, okay, to illustrate an idea. So in a distance time graph, if I have a diagonal line, let's say I want to read this point here. Okay, it means that after 1 hour from starting, the distance, my graph is not perfect, okay, the distance might be 1 kilometer. Okay, so this is how we interpret it. After, okay, maybe this one is in hours. After 1 hour from start, 1 km has been covered or traveled. Alright, that's how we read and understand the distance time graph. Then, for a speed time graph, similarly, if I have a line, okay, being drawn in our speed time graph, if let's say I have a point over here, okay, this will mean that maybe at 10 AM, okay, the object was traveling at 1 kilometer per hour. Okay, so that's how we interpret a point found on our distance time and speed time graph. Now there are other important things that we need to interpret out of a distance time graph and a speed time graph. Okay, and those are your gradient, okay, of the line as well as the area of the area under the graph. Okay, so first of all, let's look at the gradient of the line. Okay, gradient of the line itself in a distance time graph. Let's say I have 2 points. Okay, from the first point that I just indicated in red, now I put it purple. Okay, so if I have 2 points and I determine the gradient of this line over here, okay, what does it tell us? Based on our definition of gradient, which is rise over run, okay, what is our rise value? Our rise values are actually our distance values. Then after that, for our run value, it is actually our time value. Okay, so gradient itself being equals to rise over run, which is distance over time. Okay, so distance over time should be familiar to you. It is the formula for speed. Okay, therefore, the gradient in the distance time graph informs us about speed. So it is a very logical deduction. Okay, the gradient of the graph, of a distance time graph, tells us speed. But what about our speed time graph? If I have a point over here, again, okay, our rise and run. Rise is being defined by our speed here, and then run is actually our time. So gradient will actually be speed divided by time. Okay, for non-physics students, you may not be familiar with what is speed over time. Okay, but speed over time actually tells us acceleration. Okay, the definition of acceleration is the rate of increase of speed or rate of change of our speed. Okay, because it is not all the time that you are moving at a constant speed. Okay, the same speed all the time, it doesn't really always happen. Right, there might be times whereby your speed is increasing itself. Okay, so that change from time to time, that is what we call acceleration. So maybe to better illustrate the idea of acceleration, okay, for example, okay, let's say an object is currently traveling at 1 kilometer per hour, followed by 2 kilometer per hour, then after that 3 kilometer per hour next. So this change over here is an increase of 1 kilometer per hour. Oops. So this change itself is what we call the acceleration. Okay, the rate of change of your speed. Okay, so it increases by 1 kilometer per hour for the next juncture. Right, so that is what we call acceleration. Of course, we are not going to dive so deeply into the idea of acceleration. That is covered in your physics itself. Okay, the objective over here is about interpreting and understanding your distance time graph and speed time graphs. Okay, so gradient in the speed time graph tells us acceleration. Then another aspect of our graph that we need to interpret is actually our area under the graph. Okay, so let me just scroll up. All these are written in your notes already. I'm just trying to illustrate it. Okay, so I'm still having my distance time graph and my speed time graph. Okay, so now looking at area under the graph. So this is my distance time, and this is my speed time. Okay, so area under the graph. Let's say I have to look at the area under. Let me decide how should I take this. Area under this line. Okay, and it is a what shaped triangle, right? Okay, whereas compared to this one. Okay, the area under the graph for the distance time graph. Oops, area under graph. In the distance time graph, right, it will be half times base times height. And the base is actually your distance values times height will actually be the base is your time value, my bad. And then your height is actually your distance value. But just by looking at time times distance, is it meaningful? Does it make sense for anything? Time times distance is not meaningful at all. It has no meaning at all. Okay? So therefore, I'm trying to illustrate over here that in distance time graph, okay, your area under the graph doesn't tell us anything. Okay? There's no information that comes out of it. No meaningful information. Okay? Nothing to interpret out of your area under graph or distance time graph. In contrast to your speed time graph, okay, the area under the graph, by the same logic, half times base, which is your time, because this is your base, and then your height will be your speed values. And what is speed times time? Speed times time is distance, right? Oops. Okay, so therefore, our area under the graph, in a speed time graph, doesn't matter what shape is it that we are calculating, it will inform us about the distance. Let me just write this here. Okay, so area under the graph for a speed time graph tells us distance. Right? So what I have shown over here in comparison between your distance time and your speed time graph is that in the distance time graph, so if I was to zoom out, okay, distance time graph here tells us, okay, that the gradient tells us speed. Then after that, for our speed time graph, the gradient tells us acceleration. Area under the graph of a distance time graph tells us nothing, while the area under graph for speed time graph tells us distance. Okay, so we need to be clear about that. Alright? Okay. Alright, I'm going to move on. Okay, so all this information is all already stated out here. Okay, whereby I've already mentioned that speed can be found by finding the gradient. Okay, likewise for speed time graph, if I were to scroll to here on page 17, okay, your gradient informs your acceleration, area informs the distance traveled. Okay, so that's the summary of the things. I want us to dive deeper into distance time graph. So if you may listen to page 14 of your notes. Okay. So on page 14 of your notes, right, we have a distance time graph here. Okay, and there are different line segments in our distance time graph. Okay, we have a line segment that goes up like that. Then after that, at rest, or rather a horizontal line, followed by another line segment that comes down. Okay, so how did I get all this information to say that it is driving away from CTP, at rest and not moving, returning to CTP? Okay, there is interpretation from a distance time graph that you need to make. Okay, let's work on it one by one. Okay, for the first line segment, why is it considered driving away from CTP? This distance time graph is a unique one because in this case, instead of giving you numbers, they start off with this CTP over here. So what it's telling you is that over time, as you move from here to here, okay, your distance away from CTP actually increases. Right? Because at every single time point that we have here, if I were to read upwards, I will find that it comes to a certain distance here. Okay? And that distance is the distance away from CTP itself. So therefore, this line segment tells us that the driver is driving away from CTP. Okay? Then, what about this horizontal line? For this horizontal line, how we interpret it is that for every single point, if you look downwards, okay, towards the horizontal axis, for every single time frame that we have, okay, every single distance that comes out of it Okay, it's the same. Alright, so there is no change in the distance as time passes. Therefore, okay, since there's no change in distance, your object is not moving. Hence, it is at rest and not moving. Okay, so that's why for horizontal lines in the distance time graph, it is considered as at rest and not moving. Okay. Then finally, continuing with the motion that we see, it continues to come down. So over time, we see that the distance gets closer and closer back to CTP. Okay, because across time, we see that it is getting closer to CTP itself. Okay, so therefore, it is returning to CTP. Okay, so that is how we interpret this particular distance time graph. Okay. Then moving on to look at example 13. Let's read the question. It says that the figure below shows the graphs of a cyclist's journey between a certain time interval, 8 to 12 p.m. The graph can be divided into 4 sections, 8 to 9, 9 to 9:30, 9:30 to 10:30, and 10:30 to 12. The question wants you to calculate the gradient of each of the section and state what the gradient represents. Okay, so we need to observe the individual parts. Let's first look at 8 to 9 a.m. Okay, this part that I've just highlighted in yellow. So for 8 to 9 a.m., okay, how do we find the gradient? So it's the same way as for our usual calculation. Okay, finding 2 points, you can just refer to the endpoints of your straight line. Then after that, we calculate out the gradient. I know the space that I've given to you might be a little small, so you might have to reduce the size of your handwriting. So the gradient itself, understand the coordinates over here first. Okay, if you want to go and read the coordinates here, reading the x coordinate may not be a meaningful task because the x coordinate is a time value, it is not a number. Okay, so you cannot say that the x coordinate is 9. Alright, because this is a time value. Okay, so it is not going to be meaningful to look at saying that down here x coordinate is 9 and then after that y coordinate 20. Because that's not true. Okay, your x coordinate is a time value. So then how? Okay, you can then depend on your rise over run understanding. The rise over here is 20 kilometer, and then the run over here, okay, is actually a 1 hour duration. Okay, so your gradient will actually be 20 divided by 1, and that gives us 20 kilometer per hour. Because your rise is in kilometer, your run is in hours. Okay, so to interpret this, as per what we have seen just now, over time, okay, we see that the distance actually increases. So what this means about the cyclist is that the cyclist is actually moving at a constant speed, okay, and away from the starting point. Okay, let me choose find the marker. Okay, we say that the cyclist so the gradient as mentioned in the distance time graph tells us about speed. So the gradient informs us that the cyclist is moving at a constant speed of 20 km per hour. It is constant speed because there is no change, okay, in the rate itself. It is a straight line, so there is no change in the speed over time. It keeps on moving at the same speed. Okay. Then we look at the next line segment, this one that I've just highlighted in green. Okay, it is a horizontal line and we know for sure that all horizontal lines have what gradient? 0. So no calculations needed, you need to know all horizontal lines gradients are 0. Okay? So when the gradient is 0, means that the speed is 0, because we understand that a gradient in the distance time graph tells us speed. So speed being 0, it means that the cyclist is at rest. Okay? Then, over here, between 9:30 to 10:30, okay, we continue to find the gradient with the same idea that we had earlier on, marking out 2 points, observing for the rise and also the run. So the rise in this case, if you count the number of units, that is 30, because it is from 20 all the way to 50. And then the run in this case is from 9:30 to 10:30 a.m. So therefore, it will be 1 hour. Oops, okay. So the gradient, 30 over 1, so 30 kilometers per hour. Okay? So the cyclist is actually moving at a constant speed of 30 kilometers per hour. Right? I'm fully aware that some of us do physics, especially 301. Okay, and this concept is something that you have already learned. Okay, but I know that 304 doesn't take physics for all students as well. So do bear with the case. Okay, then finally looking at the last segment of it coming downwards. Okay, just take note that the gradient will have to be negative in this case because we are doing the rise over run method. So we need to include the negative sign on by ourselves. So the rise in this case is actually 50 kilometers, and the run, okay, will actually be 1.5 hours. So it is 50 over 1.5, and that will give us about negative 33 and 1/3 kilometers per hour. Okay, you might be wondering how come speed, okay, is negative in this case. Alright, that's because, strictly speaking, it can be considered as velocity, but we're not going to dive into the difference there. Okay, we just take it that speed is going to be positive. So we say that the cyclist is traveling towards the starting point at a constant speed of 33 and 1/3 kilometers per hour. So for speed itself, it is supposed to be a positive value, so we don't put in negative value. So down here should be positive. Okay. Again, constant speed, and it is actually towards the starting point. Okay. Moving on to the interpretation of all the different kinds of your distance time graph. Okay, I have already covered that in a distance time graph, if it is a horizontal line, every single time period that we have here, your distance remains the same. Okay, so there's no change in the distance, therefore you are not moving at all. Okay, so therefore we say here that the object is at rest and not moving. Okay, either you say that it is at rest or you can say that it is not moving. Right? Then, looking at the one at the bottom, I'll tackle the straight line graphs first. In this case, if I have a diagonal line going upwards, okay, at every single time juncture that we have, what we see is that the distance changes. But the distance changes at a constant rate. Okay, so the gradient is also going to be constant, therefore we say that the object is moving at a constant speed. Okay. Then now we look at the curves. Okay, let's just start with this particular curve on the right here. How do we interpret the curve? Okay, yesterday I taught you how to see tangents, how to draw tangents, right? The reason is because I need us to be able to understand, okay, curve distance time graphs. Right? So if you were to draw in tangents, for example, just to understand what's going on. Okay? The tangent at this point is slightly maybe something like this over here. Okay? And then after at this point, you see something like this. I'm drawing very bad tangents by the way. It's just meant for illustration purposes. Okay? So maybe this is the tangent over here. Okay? Over time, what do we observe about the tangents?
It's going faster.
It is getting gentler and gentler. Okay? So the tangents are getting gentler and gentler in gradient, and therefore, if it's a gentle gradient, your gradient value is smaller. So with a smaller gradient value, what does that mean about speed? Your speed is slower. Okay? So, tangents gentler, gradient smaller. Okay, and therefore your speed is slower. So what this means is that your object is moving at a decreasing speed. Okay, and also it's away from the starting point.
Is that a mobile device?
Is there something that I need to know? I don't appreciate that. Okay, so away from starting point itself. Just now I caught the word deceleration.
Yes.
Hang on, is this considered deceleration? We are not able to tell that it is decelerating, right?
Decelerate is like.
Sorry, let me just go and think about it. Okay? Your speed is getting smaller and smaller. Yes, it is decelerating. Okay. Yes, you can say that it's decelerating. Whereas your speed is actually getting smaller. Yes. Okay, so you can say that it is decelerating. So okay, but exactly how is it decelerating, you wouldn't know. Okay? Whether is it increasing deceleration or decreasing deceleration, you wouldn't know. Okay? So deceleration will mean that it is getting slower. That's the meaning of deceleration. Okay? Then going back up to this one here. Okay? So again, we observe the tangents. It starts off maybe being like that. Then after that being this way. Okay, and then after that we observe that your tangents are getting steeper. Which means that your gradient is getting greater in value. And with gradient implying your speed, that means speed is getting faster. So, in this case, we say that the object is moving at an increasing speed. Okay? And it is also moving away from starting point. Right? In other words, this is also accelerating. But we wouldn't know whether it's increasing acceleration or decreasing acceleration. Okay? Right, so it is about understanding the tangents, okay, to interpret this. Alright? Now, moving on. I'm not going to cover example 15 yet, okay, because it requires us to draw a curve. Okay, however, I want us to take a look at example 16. This is where I need your graph paper to be out. Okay, take one piece of graph paper out. Okay, so looking at example 16, it says that Michael starts a 30-kilometer journey at 9 a.m. He maintains an average speed of 20 kilometers per hour for the first 45 minutes and then stops for a rest. So a lot of information here, maybe let's just highlight some things. First, it is a 30 km journey, started at 9 a.m. Average speed of 20 km per hour for the first 45 minutes. Then it stops for a rest. Okay? Then after that, he continues his journey at a different average speed of 30 km per hour. Maybe orange is not the color. Okay? So there are 3 different parts to his journey, right? Such that he later on ends at 11:15. We want to first find out what is the distance traveled in the 45 minutes. I don't know about you, but typically when it comes to a speed question, I like to draw a diagram to represent the journey so that I have a visualization of what's happening. Okay? So, personally, I will draw maybe a timeline of some sort to represent the journey that is 30 km long. He started at 9 a.m. ended at 11:15 a.m. Okay? So in general, that is the information I have first. Then, he traveled for 45 minutes, maybe 45 minutes, 9:45 will be here. So for this segment, 45 minutes, 20 km per hour. At this part, he rested. Okay? For the remaining journey, he traveled at 30 km per hour. Okay? So I'm just trying to understand the question first. Then looking at part I. Okay? You may either write this answer on the blank space provided, otherwise you may write it at the back of your graph paper so that it is together. Okay, to find the distance traveled in the first 45 minutes, that will mean that we're looking for this part. We have the time, we have the speed, so therefore the distance traveled will be speed times time. But I want us to take note about the units that we have. So we need to do some conversion. It is much sensible for us to convert the time into hours. Okay, so that I will eventually be able to get a distance of 15 kilometers. Okay, so we need to ensure that the units for time is the same before I can compute for the distance. Okay. Now next, we want to draw the distance time graph to represent the journey. Okay. Let me just draw a sketch first before I turn to my graph paper. Yeah. Okay. I just drawing a sketch so that we can plan out how we're going to draw this. We're going to have a distance time graph. So vertical axis will be your distance. And then after that, your time axis is here. Okay. Since we are given things in time, okay, 24-hour clock, so we have start at 9 a.m. followed by maybe 10 a.m. Okay. I'll give you the scale in a moment. Okay, maybe instead of 10 a.m., maybe 9:30, 10, 10:30, 11. Let me extend this time. And then 11:30. Since we need to cover up to 11:15. And we see that the distance traveled is already up to 15 kilometers. I'll give you the scale in a moment. I'm just planning it out here first. Okay, we know for the start, it is going to be 15 kilometers travel in 45 minutes. So we can find out 9:45 maybe somewhere here. We have indicated in black. 15 kilometers, so maybe somewhere here. It is traveling at a constant speed, so it will be a diagonal line upwards. The problem here is that we do not know how long is the rest time. Okay, neither do we know, okay, what is the journey like for the remaining part. Okay, so I'm trying to draw out this sketch for us to realize that we are missing information. Okay, but can I find out what is the missing information? I can. Because I know that at the end of the journey at 11:15 a.m., it needs to reach 30 kilometers. Okay, but the problem is that I just do not know what time, okay, is the duration of rest and what time did it start. I don't know what time exactly is it over here. So I do not know how to connect this line. Okay, so we need to go and figure out, okay, how to do this calculation. Right? Let's think about it logically. Okay, this entire journey is 30 kilometers. Right? That person has already traveled for 15 kilometers. What is the remaining distance left? Remaining distance left will be 15, right? Because 30 minus away 15. Okay? We do know, actually, what is the speed of the end part of the journey, which is 30 kilometers per hour. Now I also know what is the remaining distance. So can I find out the duration? I can. So time taken for remaining will actually be distance divided by speed. So 15 kilometers divided by 30 kilometers per hour. And that will give us 0.5 hours. Okay? So I know now that if I end at 11:15 here, half an hour before that, that will mean that it is 10:45. So that means that I should be getting a diagonal line like that. Okay? And then because in between it is resting, so in the distance time graph, you expect a horizontal line. Okay, so this is how we plan out the drawing before I go into drawing itself. Because if you don't plan this out, there's no way for you to know how to even draw this distance time graph. Okay, so with this plan, okay, we draw it out on our graph paper. Okay, so now then we draw in our points, okay, or our lines. Okay, we know that for the first segment is at 9:45, that is in between 9:30 to 10, which arrives at 15 kilometers. So this is 1 point. Sorry, down here mark 0. Okay. Then after that, it continues moving at 10:45 from where he was at 15 kilometers. And then go upwards and stop at 11:15 for 30 kilometers. So eventually, your graph will look something like this. Alright? Then now in part 3, okay, the question was asking to hence state the duration of the stop, giving your answer in minutes. So, the duration of the stop, based on your graph here, will be where there is a horizontal line, and we can see that it will be 1 hour long. Okay, but because the question says in minutes, it will be 60 minutes. So for convenience, I'm just writing it directly on the graph paper. Okay, we see that from the graph, the duration is 60 minutes. Because the question asks for it to be in minutes. Okay?